I'm Romit Choudhury. I'm a professor at the University of Illinois at Urbana-Champaign. And I have 150 slides for 1 hour, so I'm not going to waste too much time talking about other stuff. Let me just quickly get started on this, okay? So why are we talking about position, location? Why is it so important? And the first and foremost reason is that location encodes a lot of rich information about any individual, any event, or any aspect of life, okay? For example, if you know a person's name, you might be able to Google that person and find out more about him or her in Facebook. If you know a person's location, you also have quite a bit of information about what this person is probably doing in this current condition. So location actually gives you a lot of rich information. Also, location is sometimes an address to which you can communicate. For example, if there's an accident on the road, you can say, please send this information to the hospital nearby, where the hospital nearby is kind of the location that you're sending the information to. This information is not addressed to a MAC address or an IP address. It's addressed to a location, which is why location is also very valuable, okay? Where do we stand today in terms of location? GPS has been hugely successful in cars and in the military, right? But there are still open problems, questions in GPS, such as energy. If you do GPS continuously, the energy of any device drains very fast. People are talking about that. People are also talking about attacks on GPS where someone can actually make your GPS receiver think they're receiving signals from a satellite where you're actually not receiving any signal. And also there have been attacks on GPS where recently the airport at San Diego had stalled for several hours because someone was actually jamming GPS signals. And the jamming device turned out to be a $10 device that you can buy from Amazon, which would actually jam these GPS receivers, okay? So lots of stuff going on in GPS, although broadly GPS has been pretty successful. But with recent, the onslaught, the revolution with smartphones, wearables, IoT, smart cars, all kinds of new applications have come up which ask for new kinds of location, positioning, tracking algorithms and techniques. And all these challenges and opportunities in localization are pretty much research questions at this point. Most of those questions have not been solved to the point that we see products in our daily lives, okay? So what are these kind of apps? So for example, you still do not have an app that would remind you while you're passing a library that you should return your library book. Why is such an app not there? Because this kind of an app which reminds you that you should return your library book when you're passing by the library requires the app to be continuously doing localization. And the moment you do localization continuously, your battery drains dramatically, and thereby when Apple launched that app, everyone was excited, but very soon the app was taken off or it was not really used anymore because the battery was draining significantly, okay? In our university, there are certain files, certain documents that you can only access, only read if you're in this room, okay? It would be nice if the system can actually figure out which room you are in and give you access based on that. That's kind of a location problem which is still not solved, which many apps would like to have. We always talk about targeted ads in Starbucks, Walmart. Louvre Museum, I know, they do want to give you information about paintings that you're looking at based on your location. So you're in this indoor environment in a museum. You stand in front of the Mona Lisa, and your phone starts telling you information about Mona Lisa. You move to the next painting, your phone gives you information about the next painting. That requires certain kinds of localization, which is still not available today. People want to do localization in terms of gestures and activity of humans. If you want to move your hands in the air, you want to take medicine, you want to understand exactly what your arm is doing, you want to create a mouse in the air, that is also a form of localization where you're localizing your wrist as it moves in the 3D environment. Those kind of algorithms are also open as of today. You want to understand human movement without wearing devices. People are working on how wireless signals could reflect on your body, and from that, the wireless systems figures out what you're doing, even without wearing any devices. Those are kind of location apps that are not available today. And finally, even augmented reality is a new emerging kind of application which requires localization. For instance, suppose you're standing at this beautiful place somewhere in California, you see this beautiful house on top of the hill, and you want to know how much it costs to live over there, right? Today, you don't have a way to really figure that out. You do not know anything about that house. This is a beautiful scenery. But people are starting to talk about applications where you take your mobile phone, you look at that house, and from that you compute the location of the house, and from that location you go to Zillow and you figure out that the house is $7.8 million, which means you have to stop research and go and do a startup. Okay? But here the point is you look at an object and you localize that object. You look at the plane and you localize the flying plane, right? These are certain kinds of localization primitives, localization technologies that many applications care about, but as a research community, we still have not been able to solve them fully, which is the reason why we think localization is a rich space for all kinds of future research. Okay? So bottom line is there are lots of applications coming up, especially in the last decade, which ask for different kinds of localization primitives or building blocks. Imagine these are the tools that you have to build certain kinds of technologies: indoor, outdoor, semantic, context, maps, humans, groups, gestures, patterns, privacy, security, everything around location, position, and tracking. And now these applications essentially give you various constraints. Some applications will say, oh, energy is a big deal for us. Other applications would say accuracy is very important to me. Some other application will say you can have energy and accuracy, but you cannot assume that you can go around and do some database and data collection and fingerprinting, etc. So there are various kinds of constraints that different applications give you. So all this put together, the space is actually quite rich. On the other hand, these are all the negative, bad news, because it seems like a difficult problem to solve. But at the same time, there are lots of sensors and devices and RF radios coming up, which put together actually give you a lot of opportunities to handle some of these challenges that are being thrown to you by the applications. Okay? So in that this is the context in which localization and tracking research is relevant. And here on, this preview, this tutorial, hopes to introduce you from first principles some of the main challenges, approaches, and techniques in the space of localization, what has been done mostly. And we'll focus on the core challenges and opportunities. We clearly don't have time to delve into the details, the algorithmic and the technical details. What I'll try to do is I'll try to give you the high-level intuition of what is hard, and is there a particular opportunity or an insight that gives us a handle to solve some of these hard problems. Okay? So it's going to be very high level, but please do stop me. I'm going to talk about lots of stuff, so please do stop me at any point in time when you think I'm going too fast, or if something seems interesting that you want to know more, we can dwell upon it a little bit more. Okay? So let's make this an interactive kind of a session as opposed to me just talking. Okay? So today's topics, I'll start with GPS basics very quickly. Then we'll talk about indoor wireless localization. Then we'll talk about indoor sensor fusion localization. Then we'll briefly talk about gestures and activity, walking, running, arm gestures, and group localization. We'll have device-free localization at the end. And finally, we'll do a rapid fire, essentially things that we've not been able to cover. With one slide, we'll kind of rapidly move through them and say, okay, these are the other things that are happening in case you want to follow up on them. Okay? Couple of caveats. This space has more than 3,000 PhD theses already, orders of magnitude more papers. So this is a heavily subsampled 1 hour, multi-lossy compressed, sub-Nyquist sampled 1 hour session. I've cited a few papers. These papers are by no means the only papers or the best papers or the first papers in the community. These are papers that quickly come to mind, that could quickly come up when I did Google searches and I cited them. These are just pointers for you to look into references in those papers and and read more about them. I'll talk about only the core challenges and ideas, and finally I've borrowed slides from my colleagues and friends as well as Googled them out, and I've used some of those slides in this 1 hour tutorial. Okay? I really have 150 slides and we're done with 10 of them, so I should move a little bit faster. Okay? Let's start with GPS. Okay? All of you know how GPS works, right? Okay? It's very simple. Actually, it's not very simple, but at a high level, there are lots of satellites moving around the Earth. These satellites send out signals continuously. You have a GPS receiver which receives these signals, and from that they compute their 3D location. Well, what is really happening? The satellites are sending a signal with a timestamp on the transmitted packet saying, hey, I transmitted this packet at 9 a.m. You receive this signal at 9 a.m. 1 second. You write an equation which says the range, that is the distance from the satellite to the receiver, is my receive time minus transmitted time times the speed of light. That's one equation. I need to solve for 3 unknowns, my x, y, and z coordinates. I have one equation, that's not enough. Therefore, I need 3 satellites, and from 3 satellites I get 3 equations. I can solve for my unknowns x, y, z as long as I know the locations of the satellite, which is precisely known from satellite geometry matrices that are available online. Okay, because the way the satellites are moving are very precise, they're very well known. Well, if you do this, you're going to get an error of 300 kilometers. Can someone tell me why? Why? The clocks that when you set TR, receive time minus transmitted time, this is only true if the 2 clocks are perfectly synchronized, right? If the clocks are not synchronized, then what do? You say, okay, I'm going to model the difference between these 2 clocks as another unknown. I don't know that. But because now there are 4 unknowns, right? Now I can say the range is TR minus TS times C plus some clock offset times C. I don't know this clock offset. But now there are 4 unknowns, x, y, z, and delta. I take one more satellite over there. I solve for all x, y, z, and delta clock, and I end up getting my x, y, z. And this is also why GPS is able to give you clock synchronization as well. In fact, many of you might know that the smart grids or many other systems that actually require very good clock synchronization, they all connect to GPS to have their clocks synchronized well. So GPS, this is the reason why GPS gives you clock synchronization as well. Okay? And this gives you 1 to 3 meters error. And this is, of course, I'm oversimplifying a little bit. There are all kinds of atmospheric delays where the signals don't come in straight, and all kinds of stuff happens. So there are sophistication over here, but broadly, this is what is going on, and this is called trilateration, meaning you compute distance from 3 different or 4 different known positions, and from that you compute your location and time offset. Okay? GPS systems is good and robust by now. However, many new challenges appearing. One is energy, one is jamming, and the other is multipath under close to ground conditions. Mostly GPSs were used where you're holding it on your hand, or military people were keeping it in their backpacks, or cars were having it on their dashboard. And then the signals that come from the satellite and the signals that reflect from the ground are reasonably close to each other. Okay? New applications are where drones are coming up, where the drones are actually reasonably high up. And that's when the line of sight path and the reflected path are actually delayed much more. And that actually makes things a little bit more complicated. In other words, with drones, the multipath issues are becoming more pronounced. Okay? So this is where new GPS research is happening, and there's a lot of new excitement in that community. Okay? But we're not going to delve too much into GPS. That should give you a high-level overview. If you're interested, please go forward and look more into those. But the question we are going to ask is, but what about taking localization, GPS-like localization, into indoor environments? Okay? And the reason that GPS does not work in indoor environments, most of you know, right? One is these ceilings block GPS signals. It's coming from a satellite, it's already weak, and these ceilings, concrete ceilings, block them significantly. And secondly, when we did those equations of range equals TR minus TS, we assumed that the signal is coming in a straight line. Right? The signal actually does not. It bends in across different parts of the atmosphere because of different densities of air. But even those bendings are not too much. But when there is a place like high-rise buildings, a place like Manhattan or a big city, the signals actually bounce a lot. In the indoor environments, it bounces a lot more. And altogether, the basic GPS techniques do not apply anymore. Actually, you do not even get the signals properly. Okay? This is the reason why GPS cannot be used in indoor environments, which brought up the question almost 20 years back, that, hey, can we do something different? And one possibility was, can we use Wi-Fi? Because 2000, the year 2000, Wi-Fi was starting to roll out, or at least people were expecting Wi-Fi to roll out as a new connectivity technology. And some people started thinking, well, if there's going to be wireless signals all around us, why not use that as a GPS satellite? Meaning every Wi-Fi access point turns out to be a new GPS satellite. Why don't we do localization with it? Okay? So that's the question we are asking, indoor localization using Wi-Fi signal strength. Okay? And the idea was very, very simple, trivial. Okay? The idea is, if you put a Wi-Fi access point somewhere over here, the signal strength that you experience from that satellite varies as you go close or far away from that access point, right? So this is kind of a heat map that shows as you go close to the access point, your signal becomes good. As you go far away, your signal becomes bad. And that's an opportunity for you to do some form of localization. Okay? And in 2000, and this has been the core idea for a variety of localization techniques. And the core idea that was initially proposed around 2000 by some folks from Microsoft Research who started this work called radar. And there the idea was, you go to every location in a building and you measure the signal strength that you get from different Wi-Fi access points. Okay? You create a table that says something like, at this location, AP1 has minus 65 dB, AP2 has minus 50 dB, and so on and so forth. You go to a different location, you measure the signal strength once again, and you create a lookup table. Okay? And then, when a new person comes into the building, that new person has this lookup table. That new person measures what is the signal strength from different Wi-Fi access points and says, oh, given my measurements, which location in the table is the best match to me? And from that, you compute what your location is. Okay? This very simple idea itself gave you almost 5 meters plus accuracy. Okay? That was pretty good actually, right? 5 meters plus. But then people started asking, so what's the bottleneck to this? Why can't you get better than 5 meters? Why? What limits the accuracy for such signal strength based systems? Someone? Variation over time for what? For multipath, right? Multipath is the word, right? So it turns out that if the signal actually degraded monotonically as you go away from the access point, then it's fine. Then actually we should have had, excuse me, we should have had perfect accuracy. But it's not that. Wireless signals are known to bounce around in the environment, from the floor, from the chair, table, our bodies, and so forth. They get absorbed due to reflection through our bodies. And as a result of that, the signal strength variation is not beautiful or not monotonic, as in as you go far away from the access point, you get weaker and weaker signals. It's not like that. You could be far away and you can still get stronger signals. You could be close, but you're blocked by some occlusion and you can actually get weak signals, right? So then people started thinking about, hey, can the scattering of these signals, right? If I'm standing over here, and let's assume that light is the Wi-Fi access point, there's a signal that comes to me directly, and then one reflects from that chair, one reflects from this projector and comes to me. Whereas if I stand here, maybe this projector has no reflections coming to me, but maybe this chair now has one more reflection coming to me, right? So if you can somehow model the scattering and the reflections and the multipath, can you say that this is actually a fingerprint of the location that you are standing at? Meaning, at every location, the scattering should be different. That is actually intuitively true, right? So if the scattering can be different at every location, why don't we somehow model that scattering as a fingerprint and use that to do localization? Okay, good. So let's talk about fingerprinting the channel. And now if fingerprinting has to work, channel fingerprinting has to work, two things need to work, okay? One, the fingerprint at different locations need to be different, obviously, right? At this chair, the reflections that I receive and should be different from the reflections that I receive at this chair. Otherwise, there's no point in doing localization, right? That's one, but that's not enough. The other thing that has to hold is that at this chair, over time, the reflection should be reasonably similar. Otherwise, there's no point either, right? Because at this, if my fingerprint, actual fingerprint keeps varying over time, then what's the point? It's hard, right? So these two hypotheses need to be true, need to hold, right? Now, while we are talking about the channel, let's quickly talk about how do we even model or think of this channel when we talk about these bouncing signals, right? So at a very high level, imagine that this access point is sending a message hello, and H is the first character that goes through, right? The direct signal from the access point goes to the, say, some receiver device, and it goes undergoes some attenuation, and therefore 1H becomes 0.8H, right? Now, at the next time step, the E actually goes from the access point to the receiver. However, the H now goes a bounced path, traverses a bounced path, and then arrives at the same time as the direct path with E. Does that make sense? When the E comes in, the delayed H also comes in and adds up together. So what you receive is really 0.5H, because this is a delayed path, which might have reflected from some surface, gotten attenuated, 0.5H plus 0.8E, because this E is the direct path that's coming to you. And now you can keep doing this, meaning the further delayed H, the reasonably delayed E, and the direct path L then comes to you at the next time unit, right? And this keeps happening, and this is exactly what the channel is doing, or the room is doing, to the otherwise clean signal that is hello. When you send hello, as a receiver, you don't get H, E, L, L, O. You don't get that. You get H, then you get some combination of H and E, then you get some combination of H and E and L, right? And so forth. So if you somehow understand what these combinations look like, you can understand what the room is doing to your signals, right? So this is exactly what is called convolution, meaning the room's channel is getting convolved with the signal that you're transmitting, okay? So to visualize that cleanly, what you can say is, look, if you just look at the H comes strongly maybe at some delay, then a weaker version comes after 0.5 nanoseconds, then another weaker version comes after 1.5 nanoseconds, and so on. So just by looking at how the H is coming to you and with how much attenuation, you can essentially plot that as 0.8 comes after some maybe 3 nanoseconds, then 0.5H comes after 0.5 nanoseconds, and so on, and this models your room, right? Or rather, this models your position in the room. Do you agree with me that if you're in a different location, this would look different, right? Because the reflections would look different, right? So this is what is called the channel impulse response, and if I can get the channel impulse response, then I really can understand what the room is doing to me at this location, and I'm going to use that as the fingerprint, right? Because depending on different locations, these bars are going to shift, these bars are going to attenuate, grow, and so forth, and that's my signature or fingerprint, okay? So it turns out when people started looking at this data very closely, it indeed started showing patterns, and these patterns, even if things are changing, turned out that these patterns have some form of stability. Why? Because even though things are changing around, not all the paths get affected at the same time, right? If someone's walking past, one multipath, one reflection path might get obstructed, but the rest are still there. If someone else blocks the line of sight, still the multipath's there. So there's some form of stability, and there's some form of difference between adjacent locations, and with this, people were able to show 1 to 2 meters of accuracy, okay? So they were able to actually show that you go to different paintings, and you actually can figure out which painting you are in front of, and some museums have actually deployed some of this, okay? In fact, people said, okay, if you can do this with Wi-Fi, why can't you do it with other modes of ubiquitous signal measurements? What other mode is there? What else is ubiquitously available Well, it turns out magnetic field is also ubiquitously available, right? The Earth's magnetic field changes at every location, really, right? But it's still, so then actually, ideally, if you use the Earth's magnetic field, you should be able to precisely point out where you are. But it's not that easy over there either. There's no free lunch, because wherever there are these ferromagnetic materials, metals and stuff, that actually pollutes the magnetic field. So thereby, the Earth's magnetic field, although it has the potential to have good fingerprint, in reality, the fingerprint is not that great, and it's somewhat comparable to what you get with RF. Okay? And people have looked at combinations of RF and magnetic field to actually combine them and do better than either of them, but the accuracies have been broadly around 1 to 2 meters. Okay? We're not going to delve more on this, but there's a lot more work over here. If you're interested, do look at them. But the question that came up on this line of research is, who went to all the chairs and collected all those fingerprints, right? In other words, in a museum, are you going to go and stand in front of every painting? In Walmart or a superstore, are you going to stand in front of every toothpaste and every milk carton and figure out what the wireless fingerprint is? That's crazy, right? In fact, for this museum, what authors did was they put a laptop on top of a Roomba, made the Roomba go around back and forth in front of the painting, and collected the wireless channel fingerprints. That doesn't scale well because your mobile phone is not going to be on the floor, so you have to really do 3D fingerprinting, which is a mess. Does that make sense? Right? So people said, no, this is not, this is nice, but this is not practical. Okay? So then people said, can location and mapping or location and fingerprinting be done simultaneously? Okay? I don't need to go and do this fingerprinting separately up front. Now that brings up this classical technique or theory which is called simultaneous localization and mapping, which is SLAM, which essentially comes from the robotics community. Okay? And what they really say is, look, I am going to go around and make a bunch of observations, measurements, let's say RF wireless measurements. I'm going to go and walk around, and I'm going to keep making measurements, and I'm not going to know where exactly I am. I don't know that, right? Originally, what were we doing? We were going to every chair, and we were saying, I'm at chair number 2, this is the wireless fingerprint that I have. I'm at chair number 3, this is the fingerprint that I have. SLAM says, I don't know where I am, but I'm just going to walk around. Okay? But after I get all the data, can I figure out the map and the location simultaneously? Meaning, this M is essentially my map or my landmarks, let's say chairs, and this X is essentially my location. Okay? So what SLAM says is, by looking at given all these observations, I should be able to figure both out. How? Basically, I update the location posterior, assuming that the map is known. If I know where the Wi-Fi access points are, assuming that is known, I figure out what my location is. And assuming my location is known, I figure out where my Wi-Fi access points are. And I can keep doing this iteratively, and it shows that it actually converges. Although it's a local optima, it actually converges pretty well under, of course, certain assumptions. Okay? So you essentially solve an expectation maximization kind of a problem, where both the variables are unknown, but by doing some kind of a gradient search, you actually converge to a reasonable optima. It is not the global optima, but it's pretty good. One way of thinking about this is, you are making many, many measurements, right? And all these measurements are saying, from this location, I see the Wi-Fi access points in this orientation or in this formation. From the next location, I see it in a similar formation. So you can think of all these as equations that are essentially trying to solve a whole bunch of unknowns. Okay? So this is actually a pretty general technique, but has been utilized, instantiated in various specific algorithms. Okay? So one algorithm that has come up in this space is called locating in the fingerprint space. And the idea was the following. This was a paper somewhere, I think, in MobiCom several years back. And it said that, look, I am going to let people wander around in a shopping mall. They're going to collect all their wireless measurements. And they're going to give all the measurements to a central location, say in the cloud. And now, what I'm going to do is the following. I'm going to say, look, we are also going to assume that when those people are walking around, we have some way to measure that they've walked this far. So if I've taken 10 steps, I have some way to measure that when I took measurement number 1, and after 10 steps I've taken measurement number 2, I have some way of figuring out how far these two locations were. Okay? So then what they do is they take all this data and they compute similarities between fingerprints. Okay? So in other words, when I take a measurement here and I take a measurement here, those two measurements should be similar. Whereas if when I take a measurement here and I take a measurement there, those two measurements should be different, right? Because the channel fingerprint should be different, right? So then they have a matrix which has these similarities. And now they're asking the question, given these similarities and dissimilarities, tell me what map can this correspond to? Or what motion pattern of the user can this correspond to? Right? So for example, right, if I give you signatures that are changing slowly, the first signature, let's call the first signature S1. Let's call the second signature S2. S1 and S2 are pretty similar. S1 and S3 are less similar. S1 and S4 are even less similar. But S4 and S3 are very similar. If I tell you that, you can start envisioning that this guy is actually walking in a straight line, no? We are switching gears over here. I'll stop there and thank you for listening in.